Hello there, this is an interview with the authors of the paper Learning What You Don't Know by Virtual Outlier Synthesis. This paper presents a method to create what it calls virtual outliers, which are synthetic out-of-distribution data points in the latent space of the model. And then it trains that model to successfully recognize these points as out of distribution. The paper performs very well on a wide variety of benchmarks, and I have actually made a comprehensive paper review in the last video about this paper. If you haven't checked that out, please do, because I'll go over the paper, I'll explain everything that's in it, and the authors that I'm interviewing today have seen that review. So we all start from a common level, and they're directly able to respond to my criticisms, which is really, really cool. So in this interview, we go over a lot of topics, but mainly I get my questions answered, and we get a bit of a look at the behind the scenes of the research, how the research came about, what the authors were interested in, how they solved problems that came up in between, and much more. I hope you liked these paper reviews plus interview things. Let me know how I can improve these videos for you by leaving a comment. Like if you do like the video, subscribe or tell someone to subscribe, and I'll see you around. Bye-bye. Hi everyone, today I'm here with Sharon Li and Shifeng Du, who are authors on the Virtual Outlier Synthesis paper and are joining me today discussing the paper and as well as my attempt at an explanation of it. Sharon, Shifeng, welcome to the channel.
Thank you for having us.
Yeah, thank you.
It's very cool to have you here. So you've made this paper. It has gathered, I think, a fair bit of attention in the community because outlier detection obviously is a big challenge, especially for security critical applications. And not only do you do outlier detection in classification where we usually see it, but in like sort of the more challenging task of object detection. So my first question would be, how did you come up with this? Because it is not an obvious idea, let's say, to even tackle this problem. Like what made you tackle the problem in the first place?
Yeah, thank you for the question. I'd be happy to share, I guess, from a little bit behind the scene on the research story, how it got started. And by the way, we're really encouraged to see the interest from the community about our work. And so, personally, I am driven to solve problems that are real, meaning that has some connection to the real world. And just like you said, I think out of distribution detection is one of those problems that really matter a lot in deploying machine learning models in the real world. And so, sometimes when we were getting closer to this, more realistic scenarios, that also means problems are getting harder and more complex. And this actually takes a trajectory to get there. It's actually reflected, I think, in how the field of OOD detection has evolved and unfolded over the years. And so if you look at some of the early research, we've done, including some other researchers have done in the space, a very common, way to evaluate how good the algorithms are based on the benchmark, which is, now similarly seems quite artificial. Like if you train a model on Cypher10 and then you evaluate against data sets such as Street View housing number or SVHN. And so the similarly simple task actually took a while for the research community to make progress on. I think over the years, we've definitely done a much, better job developing algorithms to reduce the false positive rate. And so that's why sort of, we think it's, we're at a better timing to start tackling some of the harder questions on the object detection side. And why object detection is very interesting and important, because that directly has a better connection, right? For example, if you think about self-driving cars, none of those images are simple as Cypher10, which has a single object well centered around in the scene, right? In the real world, we're going to encounter inputs that have multiple objects in the scene. And some of those are in distribution, which mean they have been exposed to the model during the training time, and some of those are not quite. And so I was, really glad when kind of Shifeng joined the lab as well to start tackling some of the questions. So that's, when we started the project earlier, actually last year already, last spring semester, that's when we started.
So you were already in the space of outlier detection, let's say, in the broad space of solving these types of problems, and then but what made you decide object detection? That's it. Did you run across a problem, or is this just a natural continuation of the classification data sets?
That's another great question. So, why object detection? So one of the, like you said, I think one of the typical, scenario when we think about where outlier detection or out of distribution detection algorithms are being used in the real world is some of the high-stake scenarios, like safety critical ones, for example, in self-driving. And that is kind of built on these object detection models, where not only we have to perform classification, but at the same time being able to localize where the objects are. So I think in terms of motivation, that just seems like a very natural, application focus to start with. And of course, we have been, like you said, we have been in this the space for working on the problem, I think, since a couple years ago. And most of the work we've done in the space are on image classification. And so in terms of solution, I also wanted to share a little bit how we arrive at this virtual outlier synthesis. So, I think the first motivation is pretty straightforward. We wanted to kind of go beyond image level OOD detection to have this finer grained uncertainty estimates that tells us at the object level whether things are in distribution or OOD. And I think figure 1 in the paper is kind of a perfect illustration for why we need object level uncertainty, right? So as you explained quite eloquently in your video, that this car is something the model has observed, which is an in distribution object, right? Whereas this moose here is something that was not exposed to the model during training. And so this picture kind of highlights the complexity that an image can contain at the same time, both in distribution and OOD object, and therefore we can't just derive an image level, uncertainty measurement. We have to, go finer grain at the object level. And so that was the first, I would say the higher level motivation on the object detection side. And then on the solution side, I want to share a little bit on how we arrive at the virtual outlier synthesis. So the algorithmic idea of this paper is largely inspired by one of our previous papers on energy-based OOD detection, which was published at NeurIPS in 2020. And so in that paper, we focused on image classification setting, but from a learning algorithm perspective, we proposed this called energy regularized learning, which in a nutshell is trying to, I see your cat there, just walking by. So in a nutshell, that learning framework tries to kind of tackle the problem of classification by not only minimizing the risks on the in-distribution data set, but at the same time, we're introducing a regularizer. And this regularizer has very similar spirit as what we're using here in this paper. And so this regularizer is trying to kind of minimizing the risk, or trying to pushing the energy surface to be as distinguishable between known distribution versus unknown distribution. And so for the image classification setting, we used this. So we use this technique or data set of outlier exposure, which relies on an external different data set, right? That's not overlapping with the in-distribution data set. So that's actually one of the requirement or limitation, if you call, in that learning framework. And that does not directly translate into the object detection setting anymore, because as you can imagine, in order to bring in a outlier data set for object detection, it's going to be tricky because you have to annotate through tons of images to make sure that at the object level, things do not overlap with our training data. And so this data collection itself is a prohibitive process. And it can be very time consuming and laborious and so on. And so that also kind of motivates us to think, well, if there's no external data we can rely on, is there any way we can devise some of the outlier data from the in-distribution data itself, right? So that's where this whole idea started, really, is to think further how we improve on top of the original learning framework that we had.
And that's how you gathered the ideas of synthesizing points that are not where the data is. Is there a connection to, I'm not sure how aware of, Yann LeCun has been pushing this energy-based learning a lot, sort of pushing energy up where data is, pushing energy down anywhere else. Do you see some sort of a connection to that?
Absolutely. And in fact, the work that I just mentioned on energy-based out-of-distribution detection that was published at NeurIPS 2020 was precisely inspired by, this whole energy-based framework from, Yann LeCun.
By the way, the plural of moose is moose. I didn't know in my video.
That's good to know.
I figured it out.
Not meese.
Not meese.
Not meese.
Yeah. So I mean, it makes sense, and you've seen my explanation, right? And I think one of the criticisms a bit that I had was, if everything's pretty in this sort of 2D landscape where you can show here's the data and there's outside the data, but it gets very complicated once you go to higher dimensions. For example, you had the picture here when you mentioned we assume that the high dimensional data are Gaussians, and how now obviously your method works, right? I think your evaluation is very thorough. You measure on a lot of data sets against a lot of baselines and so on.
Thanks.
So obviously something works here. However, do you have maybe some response to me, to someone who says there's this does not convince me that a Gaussian mixture model is appropriate for this really high dimensional data?
Yeah, I actually like that question a lot. So, one, I wanted to maybe take a step back and first just to, highlight one of the key, I guess the key insight and novelty, which I like about this paper, aside from the distributional assumption that we made here, is the fact that the virtual outlier synthesis is done in the feature space, right? This, as opposed to the original high dimensional pixel space, is already a much, much lower dimensionality, right? So what you see here, this synthesis is completely done in this later representation, or sometimes we extract this from the penultimate layer of a neural network. And so some earlier works explored, so we're not the first to kind of try to synthesize outliers. But what we've done differently is to realize, in order to regularize the neural network's decision boundary, we don't have to go all the way, right, to the original pixel space, where training a GAN model can be, quite tricky, and the convergence is going to be a challenging problem on its own. So that's one kind of step, which I think an important step that we've taken, is to look into a lower dimensional latent space, which in some sense makes this problem more tractable compared to the original data space. And now coming to the second point, I think when it comes to modeling the density of the representation space, it's actually also a non-trivial problem, right? Density estimation on its own, I think it's a notoriously hard problem in machine learning. And so when we initially approach this problem, we kind of make this, I would say, Gaussian mixture distribution is the most straightforward assumption kind of to make. And this first algorithm and framework, I would say, we kind of just wanted to show, even under somewhat simplified assumption of representation space being Gaussian, you can still do this virtual outlier synthesis tractably and train things end to end. And from an empirical perspective, as you said, it actually works surprisingly well. But that doesn't mean this has to be the only solution to it. I think there are great opportunities that VOS really opens up to, is how do we perform this synthesis in the feature space more creatively, right?
When it comes to the method itself, you have this overview diagram right here, and I've attempted to explain this a little bit. Did you find my explanation satisfactory? Is there something missing? Is there emphasis in the wrong place, or what would you add to so people really understand what's going on?
I think you did a phenomenal job explaining this whole pipeline, perhaps in a clearer way if we were have to present ourselves. One thing I wanted to maybe call out is this notion of this uncertainty loss, why we formulate this problem that way. So at a higher level, you can think of our learning framework is trying to do something more than the typical supervised learning, say training a model based on cross entropy loss. There's a bit of element in the synthesis part, which closer to this generative modeling and density estimation, which we've also talked about. And so the whole framework combines sort of, both bits of supervised learning, and also, there is some density estimation involved as well. And I think one interesting bit in the learning methodology is how we leverage energy as an uncertainty measurement, and to separate apart the known objects versus the unknown ones. And so it's somewhat a problem that's not quite as complex as trying to estimate exactly the pointwise density of p of x, but rather we're kind of piggybacking on a simpler problem of, we just want this energy to be estimated as a level set that is sufficient enough to separate these two parts of data, rather than getting every single point estimated correctly, if that makes sense.
Yeah, the uncertainty loss, you describe it somewhere
I think
here.
It's down below. Yes,
and,
right there.
And yeah, so I think I had this other comment where I said directly this loss sort of only affects sort of the classification layer. However, when you think about it, what you could do is you could simply take your Gaussian mixture model, right? And you could simply have your data point there, and you could say, well, if it's unlikely, it's out of distribution, right? I could simply map my inference data point and then evaluate it according to the Gaussian mixture model that I have at training time. And I say, well, it's low likelihood, it's out of distribution, gone, right? I wouldn't need all of this thing, which tells me that this loss does more than just, modify the last layer bit. So there is is it fair to, or is this correct, my assumption, that there is like this downstream effect on the entire model? How would you, like, intuitively, adding a loss like this, what does it do to the whole, the whole feature extraction pipeline that leads to the latent space?
Yeah, that's a great question. So perhaps to answer a bit more to that, do you mind scrolling up a little bit? I think we have Perfect. Yes, that posterior probability right there. So keep in mind this whole training is done in an end-to-end fashion, right? And then whenever we have an input object that goes into this network, we are optimizing for this loss, and this loss will be backpropagated all the way, right, through this entire convolutional backbone in this object detector. And so this objective L uncertainty is trying to kind of separate apart in terms of this energy. And we'll get to this interpretation of the energy later on. But at the very high level, it's trying to just push energy to be two sides. One is above zero, one is below zero, right? And if we look at this connection with respect to this posterior probability here, so we can interpret energy as this density function for that data point p of x, perhaps plugged in with some unknown factor that we don't know, right? And so this energy does not precisely capture this density just yet, but during this optimization process, we hope that through this propagation and minimizing this objective, that this whole training would converge to a point where the density could be more separable between the ID object and then the OOD object. Yeah. And so that's the inherent connection between, the uncertainty measurement to the density.
Yeah. So you sort of want, maybe reformulate it a bit, you want to coerce the feature extractor almost to give you a space where you can be more certain about in-distribution data, but then correct, like the less certain about out-of-distribution data.
Exactly.
So this is naturally it is a harder problem, right? If you go back to this, even in the two-dimensional case, I mentioned this is like to separate three classes, I need three lines, right? But to separate three, clusters of data from their surroundings, I need like a very, decision boundary that's shaped,
and highly complex,
high dimensional, right? Yeah. And so on. Do you what are the trade-offs here that I make? Are they severe, or did you find, this works without severely impacting my accuracy as such? What's sort of the, like, what do I give up when I employ this method?
That's a great question. So I think there's natural trade-off would be to say, if we employ this regularization, does that kind of hurt the performance, compromise the performance on the object detection side, right? And so we actually showed in the evaluation part in table 1, if I recall correctly, that this whole learning framework actually achieves, both quite effectively. I think it pretty much preserves the MAP. Mm-hmm. So that's on the rightmost column, where we show on the original, Pascal VOC and Berkeley Deep Drive task, how is that MAP, changes. It's pretty much the same or similar as the vanilla FastStar CNN without adding our uncertainty regularizer. Mm-hmm. And so overall, this learning framework kind of provides an actual layer of safety net by pruning out some of the OOD object, but at the same time, if it's indeed an in-distribution, image, it can do as well.
Can you maybe, when we're at the experiments, I did not go into that at all in my explanation. Is there things that you want to particularly highlight, or what should a reader of your paper take away from the experiments, other than you beat all the baselines, which I think we've come to expect a little bit from machine learning papers? But what should like a reader take away as sort of conclusions from your experimental section?
Totally, I like that question a lot, and I think part of the ablation in the paper is, I think it's quite interesting. Going beyond table 1. We actually, did some of the ablations comparing to different synthesis strategy. And so I think table 2 is perhaps, table 3 as well. Table 2 is one of the interesting ones where we kind of try to contrast with, in terms of synthesize, we wanted to know, whether this Gaussian-based sampling is the optimal one. There are, works have done in the past, for example, directly using GAN to generate images, or you could also do mix up to have this interpolation in the pixel space as well. And then they're also, utilizing noise. I think those are all kind of natural alternatives for, our outlier synthesis approach. So I think this is one of the ablations I personally, quite like. And I also want to call out the fact that there is one previous paper, I think they used these proposals with the large background probability as the kind of the negative samples to regularize the model, and that turns out to be also suboptimal compared to using VOS.
I've also, so you had this decision to in the very last layer introduce these virtual outliers, and I think in the video I observed something like, okay, that helps if the out of distribution data really looks different in the last layer. However, if I have out of distribution data, but that exhibits the same kind of low level features as in distribution data, that might not be the case like in a vanilla network. Is this also, let's say, a weakness of your method, or would you expect that your regularizer would sort of automatically map these types of outliers to different, like would construct the latent space such that they are different? Like, is it different? Yeah.
That's it. Yeah, for that question, perhaps I can defer to Shifeng. I think Shifeng has some good answer to that question.
Oh yeah. So actually, I want to answer this question from two perspectives. So, first perspective, I think you are like mentioning some like when a model actually encounters some near in distribution OD objects. So how does the feature space functions to prevent the model to predict high confidence predictions? So basically, we can potentially adjust the sampling threshold in VOS to see whether we can create a tighter decision boundary in order to separate those in distribution objects and those OD objects. And in addition, I think near in distribution OD detection is essentially a very hard problem, and there's a couple of works exploring this direction, but they are totally in the classification setting. So perhaps we can explore how to combine a VOS with those techniques in the future. So this is the first perspective. I think from the second perspective, I'm mentioning you're like saying that how can we like look at different semantic spaces, like different layers of features. Actually, I remember we in the paper, actually in the appendix section, we have reported the OD detection performance using the layer rather than the panoply layer for outlier synthesis. And actually, it seems like the performance is not as good as what we have for if we use the panoply layer as the semantic space for VOS. So basically, I think the reason is that the later layers in the neural network might be more discriminative for classification. So those more discriminative layers may be better for OD detection and outlier synthesis, because those synthesized outliers relies on the quality of those estimated covariance matrix and then those mean embeddings for each in-distribution class. So I think that may be the reason for why we choose to use the panoply layer for
Yeah,
VOS.
I mean, it makes sense. As you go earlier and earlier, the less you can probably describe the data using sort of this sort of a mixture model approach. So I think it makes sense. I was just wondering, and even I think it's important to remember that we're still in high dimensions, and with being in high dimensions, it means that even if some of the features are the same, the moose will have 4 legs and so on, it will kind of look like a dog, but not fully, right? So you'd still expect this in these high dimensions to be separated. So maybe a bit to the research process, right? You thought of this, you thought you're going to tackle this problem and so on. Could you maybe share a bit of how the process, I think it's always, you just see the paper at the end, and the paper is like, oh wow, you have some examples here. I didn't even, I think, show them much in the video. So here you have comparisons at the bottom. Everything that's green is detected as out of distribution, which is really nice. The helicopter, I think, was one of the most shared pictures of your paper. This looks really nice, right? I think what people don't see much is the process behind it. Like, could you describe it a little bit? Was there a time when you thought this wouldn't work or doesn't work, or you don't know how to go further? How was it like to achieve at a system or arrive at a system that finally works really well?
Oh, totally. I'd be happy to, speak on that. Perhaps Shifeng can add on later as well. I think just like many other research process, nothing works out of the box immediately, right? I think part of the research, the fun is really kind of going through the process of figuring out, a lot of intermediate obstacles. And so to give you some example, right? Some of the challenges, I think, really Shifeng did a lot of hard work in the process. Just when we started the exploration, the first challenge, we have to overcome is what's the right evaluation, right? How do we get this correct evaluation benchmark? Because a lot of the previous work focused on image classification. That's more or less well established. And in order to evaluate this new setting, we have to actually gather and clean all of these, for example, OOD test images as well. So that's some of the things you just have to kind of go through and during the research process. And I think on the methodology side, there are also the challenges as well. So one thing I want to share is there's actually one hyperparameter in VOS, which is I think called the starting epoch. Which is when you start adding this regularizer. And so it turns out if you just train this whole, entire loss with the, object detection plus the L uncertainty from the start, things are not converging as well. And so why is that? Because at the beginning of the training, right, the representation is not quite well formed yet. And so therefore, estimating this density in the latent space is not also very reliable, and not to mention the sampling part. And so that's where we kind of got a little bit stuck on is, the performance, if you train from scratch, is not really as desirable. And so later on we figured out is, why don't we wait until the representation becomes, more formed. And so this idea of kind of starting in a kind of later training process helped, right, resolve this issue. And so that's, kind of another example.
But how did you get this idea? Did you have some indication from some metrics that you logged, or did you just, sit there and just try 10 different things and this one was the one that worked? Or, I imagine you sit there, you try it and stuff doesn't converge. Like, it's just like, well, it doesn't work. What can lead you to come up with the correct solution?
I think for this one, perhaps it's more natural because, if you think about how the method works, it has to rely on some embedding space that has a somewhat clear structure that you can perform density estimation and then sample from. And so when things, kind of doesn't work out, one of the, we look at what are the kind of possible major, red flags that could happen. This one would be, the kind of the top one we are diagnosing into.
Excellent. Yeah, I think that's a pretty neat overview. Is there something else that you'd like to share about this? Anything that we haven't touched on, maybe? Anything that you want to specifically highlight?
Yeah, I think I've talked a lot. Shifeng, do you want to add anything that you particularly wanted to add on to?
I think I don't have any further comments. Sharon has covered comprehensively about this paper.
Is your code is online, right?
Yep.
So people can get into it, can experiment with it. Yeah, I think that's pretty neat. Yeah, and with that, Sharon, Shifeng, thank you very much for being here, and this was very enjoyable.
Yeah, thank you so much for having us again. It's been fun, chatting about the work and so on. Thanks for inviting us.
Thank you.